Okay, so good morning and happy Monday to everyone. We're going to look today at some applications of the Gauss Elimination Method. And in fact, we will see how to find the inverse of a matrix. And we're also going to see something which is also very, very important, how to extract a basis from a set of generators of a vector space. Please mute yourselves. Who is this? Rahman. Okay. So, how does this work? Well, first of all, and I'm looking at the homework that I have posted for Wednesday. There is one homework problem which is very, very simple, but I would like to clarify it. And, or actually the first two parts of the problem, that if you have a square matrix, an n by n matrix, yeah, email it to me. Yeah, that's fine. In PDF format, please. So if A is an n by n matrix and P of X is a polynomial, then P of A can be defined. So what do I mean by this? So let's say that A is 2, 1, -1, 3. And you have that P of X is 3x squared plus x minus 1. Then you could take P of A to be 3 times A squared plus the matrix A. And now, anytime you have a constant, actually, let me make my constant 4 here so that it's a little more interesting. So I'm sorry for the mess. So let me make this 4, and you will subtract -4 times the identity matrix. And this will be P of A. Okay? No, we're going to do similar problems to the quiz. So I mean, we're going to do Gauss elimination method today a lot. Okay, so there's no need to solve the quiz. You can always come to my office hours in case you want to, or wait for it to be posted by the TA. Also, the other thing that I would like you to know is that, and this is the notation that we have introduced before, is that if A is, and I'm sorry, here I should say that it doesn't end here. You need to actually go and do the computation. So you have to multiply the two matrices, have to add to 1, -1, 3, minus 4 times I, that would be 4, 0, 0, 4. Let's do it. Let's see what we get here. So it's 3 times, what is it? It's 5. 5. No, it wasn't 5, it was 3. Sorry about this. 3, 5 minus 5 and 5 plus, let me add these two matrices at first. So what do I get? Minus 2, 1, negative 1, and minus 1. And eventually, this will be 9, 15, minus 15, 15, plus negative 2, 1, negative 1, negative 1. And this will be equal to 7, 16, minus 16, and 14. And that's the matrix P of A for this particular polynomial. Okay, then I would like to note that A with a T, according to the notation that we have introduced for vectors in Rn, this is A with the rows turned into columns and the columns into rows. So for example, if A is 2, 1, 3, 1, 5, negative 7, then A transpose, we're going to call it the transpose of the matrix, as we have seen so far. So the first row becomes the first column, right? And the second row becomes the second column. And that's it. Okay, and the nice thing is you can always multiply A transpose A and A times A transpose. You're not going to find necessarily matrices of the same dimensions unless A is a square matrix. Otherwise, for example, in this specific example that I gave you, if you find A transpose times A, can anybody tell me what the dimensions of this matrix are going to be? What kind of matrix is A transpose A going to be? So how many rows?
3 by 3.
Very good, 3 by 3. And A times A transpose is going to be 2 by 2. Okay, but if your matrix is a square matrix, then they're pretty much the same. I'm sorry, they're the same. They have the same dimensions. They're not going to necessarily be the same. So it doesn't mean that the matrix commutes with its transpose. That's not true. Okay. Now, as I promised you, let's do examples of the Gauss elimination method, and we're going to see them in the context of applications. So a first application is to find the inverse of a matrix, and or to figure out that the matrix does not have an inverse. You will do both of these things. So let me start with a 2 by 2. So let's say that I have 1, 3, 4, 2. Let's say that this is my matrix. One second, there is a question on the chat. As I said before, please always send your questions on the chat to everyone. Right, so if it goes a 3 by 3, then you would have had the one in the main diagonal for 3 by 3 matrix and 0 everywhere else, multiplied by 4. Now, the question is, what is the inverse of this matrix? Okay. And there is an amazing solution.
Minus 3 and the minus 4 1. Yes.
Yeah, it would be the matrix. You were just asking me what 4I3 would be, and we said 4I3 would be 4, 0, 0, 0, 4, 0, and 0, 0, 4. Okay. So the question is to find the inverse of A, or to figure out that it doesn't have an inverse, because we said not every matrix has an inverse. And later we're going to see a very nice condition for when a matrix has an inverse. How do we do this? The solution to this problem is an amazing one. It looks like magic. Okay, but then again, modern science does look like magic, right? Here's how you do it. So you take your matrix and you juxtapose it with the identity matrix. You put the identity matrix on the right. So far, so good? Okay. And now what you do is you apply Gauss Elimination Method to the matrix on the left. So let's see how I would do that. So first of all, I already have my pivotal right here. If I didn't have my pivotal, there would have been two cases or maybe three cases. Either my first column would have completely consisting of zeros, in which case, what do you do when a column consists entirely of zeros? What do you do in the Gauss elimination method? Or rather the part of the column that you're working with. So let's say you have worked with the first two rows, and now you're on the third column, and the third column starting with the third. So imagine the following situation. So you have already worked with the first row, right? You have already worked with the second row. And then you look at the third column, and what do you see? You see you have all zeros here. What do you do if you have all zeros? No. Don't think in terms of systems. If you have no, and again, it doesn't mean that it doesn't have a solution. Whether it has a solution or not no, we don't add anything. We can't add stuff to our matrix. So my question is, you do your elimination method. So you're done with the first column. You're done with the second column. And now on the third column, you see this picture right here. Remember that we said you're working with this part now, which means that you don't have anything non-zero to work with. If you had something which was non-zero, then you would put it on the top. You would make it pivotal, and then you would continue. But here, there's nothing non-zero. So what do you do?
Do you move on to the next column?
Excellent. That's it, that you do exactly. So you move on to the next column. Very good. Sure, the identity matrix is the one that has ones on the diagonal and zeros everywhere else. And allow me to add that always review the recordings and take notes of those things. That was explained in the recordings, but I'll be happy to give you the reminders. So great. So let's apply the Gauss elimination method here. So the first thing is I'm eliminating the 4, right? So I have my pivotal, I'm eliminating the 4. So how do I eliminate the 4? Can anybody tell me what row operation I need in order to eliminate 4? Excellent. Minus 4R1 plus R2. So I apply this. Remember, don't put equalities. The first row remains as it is, and this becomes 0. Then negative 4 times 3 is negative 12. Plus 2, that's negative 10. Then negative 4 times 1 is negative 4. Plus 0, that's negative 4. And then negative 4 times 0 is 0 plus 1 is 1. I'm getting this. And I have eliminated everything below the first, the pivotal on the first column. What do I do next now? Anybody, what do I do next? In particular, can you tell me what the next row operation will be so that I proceed properly with the minus 1/10? Minus 1/10 times what? Times row 2. Excellent. Excellent. So what I do is I turn negative 10 into a pivotal. Why? Let's explain it. Because we're done with this. So we work with the leftmost column of what is left. What is the leftmost column? Simply the number negative 10. What do we do with negative 10? We make it pivotal. So negative 1/10 times row 2. And this will give you 1, 3, 1, 0. 0, 1. Negative 4 over negative 10 is 2 over 5. And negative 1 over 10. So far, so good? This is row echelon. We're done. If all I asked you to do was, or if all you wanted to do was to find the row echelon form, then you're done. That's it. You're done. But we will do something extra here. In this case, in the case of finding the inverse, we want to get to reduced row echelon form. What is the reduced row echelon form? So it's something a little more precise, a little more stringent than the reduced row echelon form. What is the reduced row echelon form? So this means that we eliminate also eliminate everything above the pivotal elements. Above the pivotal elements. So every time you have a pivotal element, you eliminate everything that is above it. Which columns have pivotal elements here? Which columns have pivotal elements? The columns that have pivotal elements here are this one and this one. These two columns have pivotal elements. So don't bother with any other column. If this was a system, this didn't come up as the matrix of the system. If it was a system, then you would have had X, Y, Z, and Z would have been a free unknown. Why would it have been a free unknown? Because there is no pivotal element on that column. Okay, the last column would have been the column of the constants. But I didn't say this came from a system, right? This came for another reason. So what am I supposed to eliminate? I'm going to eliminate just this. So how do I eliminate this? You use R2. So minus 3R2 plus R1. Okay, and what will happen? The second column remains the same. So you get 0, 1, 2/5, negative 1/10. And the first column becomes I'm sorry, in the first row becomes 1. This becomes 0. Then you have negative 3 times 2/5 is negative 6/5 plus 5/5 is negative 1/5 right here. And finally, you have negative 3 times negative 1/10 is 3/10 plus 0, that's 3/10. Okay? And now we're done. Now, the matrix on the left is in row echelon form. The matrix on the left is in row echelon form. And here's the magic I was talking about. This matrix is the inverse. Ta-da! Okay, so let me recap. Whenever you have a square matrix, only square matrices can have inverses. Okay, only square matrices can have inverses. So when you have a square matrix, I did this row operation. So I wanted to eliminate these 3. I want to make it 0, right? So I performed this row operation. The matrix on the left became the identity matrix. Okay, the matrix on the left became the identity matrix. So what do you do to find the inverse of a matrix? So somebody gives you the inverse of a matrix. I'm sorry, somebody gives you a square matrix. What do? You take your matrix, you write it as the matrix and the identity matrix next to it. So you pretty much add as many columns as the number of columns of the matrix already. And then you apply Gauss elimination, and two things will happen. Either you will not get the identity matrix because there will be a column that will not have a pivotal. Okay, there will be a column consisting of all zeros. So you will not find, or you will get to a situation where you have the identity on the left, whatever appears on the right, that's the inverse of A. Okay, whatever appears on the right, that's the inverse of A. And I'm going to explain to you why this crazy thing is happening. But for the moment being, I want us to learn how to do it, and then we're going to wonder about why it's happening this way. Okay, so I would like you to do an example now. So find. The first option was that as you do your elimination method, you find a column that doesn't have a pivotal. Then in that case, there is no inverse. Okay, there is no inverse. Yeah, all zeros or all zeros from one point forward. So at some point, if you find a column, the first time that you find a column that doesn't have a pivotal, you stop right there and you don't continue anymore, and you say the matrix is singular. So find the inverse, if possible, of -3, -6, -9, 1, 2, -1, 2, 1, 0. Okay, so work with this 3x3 matrix. Okay, I'll give you a few minutes, then we'll do it together. Let's do it together. So what do I want? I want to create a pivotal element first, right? So how do I create my pivotal element? I already have a non-zero number. I just divide by it. And here's my nice pivotal element. Okay, now let's eliminate everything. Yeah, absolutely. You can swap rows 1 and 2. Absolutely. Yeah. Usually, so for example, if we were writing a computer program, we would have to decide on one strategy. So, and any of the two is fine, I think, for this particular matrix. Eventually, you will find the same inverse, so don't worry about it. So now we can eliminate.
Excuse me. Do we should to put the identical?
Yeah.
Zero
Sorry, I forgot about that. Yeah, absolutely. Thank you for reminding me. I got all excited about the Gauss elimination. Of course, we have to do this. Because you need to create the number 1. That's why you multiply by 1/3. How else would you go from 3 to 1? The only number you can multiply by is 1/3. So 1/3 row 1. Now I can eliminate at the same time. Actually, when you use the Gauss elimination method, last time I did it one at a time, but now I hope you can see that you can do minus row 1 plus row 2 and eliminate the number 1 from the first column, the second number 1, and then you can do minus 2 row 1 plus row 3 and eliminate. So you can do all the eliminations on the first column at the same time. That's a good tip. Okay, I'm not going to go any faster than this ever in this course, but these two eliminations can be done at the same time. So 0, 4, 2, negative 1/3, 1, 0, and then 0, 5, 6, minus 2/3, 0, 1. Okay, that's what we get. We're done with the first column. So what do we do? Where do we focus our attention now? We focus our attention right here. Remember what we said. When you're done eliminating one column, you proceed to the next part, the part on the right, and also the part below the row that contains the pivotal. Okay, you completely ignore, at least for the row echelon form. When you do the reduced row echelon form, you will need to also reconsider those rows. But for the moment being, and this is the most important part, when we do the row echelon form, we're going to forget about this. So what do I want to do first? Do the 4 pivotal. Again, if you do 4 minus 5, that might end up being a better way of doing it. But I want to do it in a generic way. So I'm going to do, which means I will have to work with denominators. 1/4 row 2. And this will give us 1, negative 2, negative 3, 1/3, 0, 0, 0, 1, 1/2, negative 1/12, 1/4, 0. And this remains as it is. And what do I do now? I eliminate 5. I eliminate 5. So minus 5 times row 2 plus row 3. And this gives you what? 1, negative 2, negative 3, 1/3, 0, 0, 0, 1, 1/2, negative 1/12, 1/4, 0. And then I have 0, 0. And I have minus 5 halves plus 6. Minus 5 halves plus 12 over, minus 5 halves minus 12 halves, plus 12 halves. So that's 7 halves. And then I have minus 5 over 12 minus 2/3. So that's minus 8 over 12. So 5 over 12 minus 8 over 12, that's minus 3 over 12, which is minus 1/4. And then I have negative 5 over 4 here. And then I have 1. Right? Okay. So now I need to make that 7 over 2 pivotal. So I need to multiply by 2 over 7, the third row. So that will be 1, negative 2, negative 3, 1/3, 0, 0, 0, 1, 1/2, negative 1 over 12, 1/4, 0, 0, 0, 1. And this will give me minus 1 over 14. Minus five over minus 10 actually. No, minus 5 over 14. And 2 over 7. Right? And this far, I mean, if I go into row echelon form, this is row echelon. This is row echelon. Okay, somebody might say, well, we haven't worked at all with the last 3 columns. Yes, because we ran out of rows. Right? I mean, supposedly now we should be using this part, but this part is empty. Right? So we're leaving behind us the first 3 columns and the first 3 rows, and there's nothing here. So this is row echelon. This is row echelon. But so now we know that it has an inverse. At this point, we can say the matrix is invertible. We know that now. We're not done finding the inverse, but we can say that the matrix is invertible. Okay, so what do I need to do now? Eliminate. I will start with the third column. You need to have so let me say it once more. For the matrix to be invertible, you need to have pivotal elements on all the columns, on all the first columns. Okay, the first n columns. Okay, you will never, I will never give you a 4x4 example here, so it will be basically 2x2 and 3x3. So if it's 2x2, I need pivotals on the first 2 columns. If it's 3x3, I need pivotal on the first 3 columns. Okay, and here you will get row 3 plus row 1 to eliminate that negative 3, and negative 1/2 row 3 plus row 2. Okay, so what do we get? We get 0, 0, 1, negative 1 over 14, minus 5 over 14, 2 over 7, and this will be 0, 1, 0, and then what do we get? We get 1 over 28 minus 1 over 12. Okay, this, this is not going to be necessarily, so negative 1 over 28, 1 over 28 minus 1 over 12. That's what I'm getting. What is the least common multiple of 12 and 28? It's 84, right? So this will be 3 times over 84 minus 7 over 84, which is going to give you minus 4/84, which is the same thing as minus 1/21, right? So minus 1/21 here. And if now you're wondering to yourselves, oh boy, are we going to have these kind of things on exams? The answer is no. I will give you very nice numbers on exams. So then you will have 5/28 plus 1/4. That's 12/28, which is 3/7 right here. And finally, I have negative 1/7 here. And let's see what else I get. So I will get 1, -2, and then actually the negative, yeah, and 0 here. And I have negative negative 3/14 plus 1/3, which is the same thing as minus 9/42 plus 14/42, which is 5/42, right? So 5/42 here. And then minus 15/14 here. And finally, minus 1/7 here. No, minus, or rather 6/7 there. Okay, one more. What is the last one? We need to eliminate that -2 on the second column. So what do? We do 2 row 2 plus row 1. Okay, and that should give us the inverse. And look, I wouldn't be surprised if I have committed a numerical error in all this. Like I told you, usually the examples that you're going to have are going to be much simpler. I did want to do a generic example right now, and I'm paying the price for it, but I did want to do that. So this will give you 1, 0, 0 here, and then you have negative 2/21 plus 5/22. That's negative 4/42. So that will give you 1/42 here. And then you have 6/7 minus 15/14. That's 12/14 minus 15/14. So that's negative 3/14. And finally, you have minus 2/7 plus 6/7. That will give you 4/7. So if everything is correct, and I'm putting a big if there, we have found that the inverse matrix is 1/42 minus 3/14, 4/7, negative 1/21, 3/7, negative 1/7, negative 1/14, minus 5/14, and 2/7. That's the inverse of the original matrix. Okay. Questions, please. I would like to give you an example of when the inverse doesn't exist. So take a look at this. 1, 4, -2, -8. Take a look at this matrix. Okay, and let's say that you were trying to find the inverse. So what would you do? You would juxtapose it with the identity matrix, right? And then you would do your elimination. So I have a very nice pivotal on the first column. It's right on the top. So I do 2 row 1 plus row 2. And this gives me 1, 4, 1, 0, 0, 0, 2, 1, right? And now now I'm supposed to work with this part, right? And I want a pivotal right here. Yeah, but this is 0. There's no pivotal. The second column doesn't have a pivotal. So what is my conclusion here? I stop right here and I say A is singular. I remind you that singular is the opposite of invertible. A is singular. Okay, so that is what would have happened. So as long as you can find pivotal for all the columns that you need to work with, that's great. If you can't, then you're through with it. Yeah. Questions? Let's take our break. And when we come back, we will do our so because we cannot find the pivotal on the second row, on the second column to be more precise, because then you could go, you could work with the third column, but you don't want to work with the third column here. That's the point. The point is that you want to work with the first n columns, with the first 3 columns. Since you don't have a pivotal on the second column, that's the end of the story. Okay, so actually, this is an excellent question. Somebody might ask here, so does that mean that our Gauss elimination method is done with? No, it's not done. At this point, nobody says that you're done, but you failed to find the pivotal on the second column. So normally now, you would move to the third column, and on the third column, you would have a pivotal because you have the number 2, right? Do you all see that? Yeah, but that's not no good. Because remember, unless you get pivotals on the first n columns, in this case on the first 2 columns, you will not be able to make the identity matrix show up on the left. And that's what you need. You need the identity matrix to show on the left. If it doesn't, if you can't do that with row operations, then it's not inverted. Okay? Okay, please take your break. Okay, so welcome back, and let me actually emphasize here one of the points of the Gauss elimination method. That basically your goal on the first column is to see this situation, right? So either you will see this situation and other stuff, or you will see this situation. There's nothing else. So either 1 and all zeros, or that, right? This is the very first step. I just want to emphasize how simple is the Gauss elimination method. Once you have done this, you work with this part, and you want for this part to see the exact same thing. It's that simple. The Gauss elimination method should be taught at the 5th grade, not at okay, 6th grade. No, 5th is fine. Okay, not at in college. Okay, this is how simple the Gauss elimination method is. Okay, that's what you do. It's a complete no-brainer. Okay, so in other words, I'm going to look here, and either I'm going to establish the same thing, either I'm going to see N1, 0, 0 here, or I'm going to see a 0, 0, 0 there. One of the two. If I see, if I can have it 1, 0, 0, I do it. possibly by bringing on the top an element that has a non-zero entry, a row that has a non-zero entry, or if I see zeros, I move on to the next. Are there any questions, please? In other words, let me put it this way. Let me put it this way. Unless you understand that the Gauss elimination method is a brilliant, albeit trivial method, there's nothing to it, then I'm afraid you need to do more work on the Gauss elimination method till you realize how trivial it is. Okay, that's if you like the benchmark. If you reach a point and you say, yes, the Gauss elimination method has to be the simplest mathematical method that ever existed and possibly the most brilliant among among methods that are this simple. Otherwise, you need to do more work. Okay. So, but we're going to do more work together. And let me put it this way. So imagine, and you will see that the second problem on the homework is that the third problem on the homework for Wednesday is exactly what I'm going to do right now. So suppose that the vectors (1, 3, -2, 2, 2, 1, 0, -1, and 5, 5, -2, and 0 span the subspace V for R4. V of R4. Find the basis. Can anybody tell me, so I have three vectors that span the subspace V. Why do I hesitate to say that they form a basis? Why do I hesitate? So I have these three vectors, they span a subspace of R4. This means the subspace consists of all linear combinations of these vectors. Can anybody explain to me why am I stopping short exactly? I don't know whether they're linearly independent or not. So now I'm going to show you how, again, it's a no-brainer, how to find how many of them you really need. Here's how you do it. The first thing that you do is you form a matrix that has those vectors as its columns. Everybody with me so far? So you form a matrix that has these vectors as its column. Then you turn it to row echelon form. So let's write this. It's so simple that we can write it. So to extract a base, to extract a basis, we form a matrix that has the vectors as its columns. We perform Gauss elimination method Exactly. It will be a 4 by, because I want the vectors to, this is 4 by 3. I'm sorry, why do you say it's not 4 by 3? This is a 4 by 3 matrix. We perform Gauss elimination method, but we said that the vectors are going to be columns. Then we say they're going to be columns right here. It says column. Why would you put them as rows if we say they're column? Okay. So we perform Gauss elimination method and bring it to row echelon form. the columns that have pivotal elements correspond to the SOC 4 basis vectors. Okay, that's how we get it. Okay, so it's a one-liner. Do Gauss elimination method on the matrix and figure out which columns have pivotal elements. Let's do it. Let's do it. So I have my first pivotal on the top. I will eliminate the 3 elements below it. How do I do that? -3 R1 plus R2 to eliminate 3. 2R1 plus R3 to eliminate -2. And -2 R1 plus R4. Do you all agree that these are the 3 row operations that are going to eliminate everything below the pivotal element on the first column? Okay, again, let's take things step by step. Remember, I told you, you will either make the column is either already 0, 0, 0. Okay, the column is either already 0, 0, 0, or if it has a non-zero entry, you will end up making it 1 and then all zeros underneath. Okay, here you obviously have non-zero elements, so you will turn it into 1 and 0, 0, 0 underneath. So let's see, 1, 2, 5. 0. -6 plus 1 is -5. -15 plus 5, that's -10. Then it's 0. 2 times 2 is 4 plus 0, it's 4. 2 times 5 is 10, minus 2 is 8. And finally, this is 0. -2 times -2, that's -4, minus 1, that's -5. -2 times times 5 is -10 plus 0, that's -10. So far, so good. Check their operations, please. Okay, what do I do next? Let me again say in detail what I said before. You want now to leave behind the column and the row you have worked with. So you're going to work with this matrix as if this is your only matrix. Everything else will stay the same. So and what do? I want to make that -5 on the first column. I want to make it pivotal. How do I make it pivotal? -1/5 times row 2. Okay, so what do I get? I get 1, 2, 5, 0, 1, 2, 0, 4, 8, 0, -5, -10. Any questions so far, please? Questions? Let me put it this way. You ask me if the fact that we have two identical rows makes it an issue. Why would you even want to look at that? Remember what I told you a moment ago. This is a completely trivial method and a no-brainer. You don't want to look at that. Okay, you don't want to look at that. You want to have your pivotal and eliminate everything below it and not think about it. Okay? It will resolve itself. The question that you ask is going to answer itself. Remember what I told you a moment ago. If the Gauss elimination method is not executed in a completely trivial manner so that you don't have to think, then you need to look at it more. Here, I'm not even looking at those things. I'm not even looking at the question that you asked. I'm going to say, don't ask this question. I know I shouldn't be saying that in the sense that every question is valid, but this question is in some sense the wrong question to ask when we perform the Gauss elimination method. Okay, it's very meaningful, actually. It's a very nice question. However, it contradicts what I told you before about making this into a complete no-brainer without thinking at all. So now what do? I need to eliminate these two, right? So what do? I do -4 times ρ 2 plus ρ 3, 5 ρ 2 plus ρ 4. So what do I get? I get 1, 2, 5, 0, 1, 2, 0, 0, 0, 0, 0, 0. Yes. Okay, so now I'm done with my second row and second column. Where do I go? I go here, right? And what do you see now? All zeros. If you have all zeros, what do? You move to the next column. Yeah, but there is no next column, right? So we're done. So this is row echelon. This is row echelon. And I hope that this answers the question that somebody told me about the quiz. This is very similar to the quiz. Well, the quiz goes 3 by 3. This is 3 by 4. But that's what you do. Okay, so we're done. What are the pivotals? Circle the pivotals. 1, 2. Okay. So these are the columns that correspond to the pivotals. So what is the answer? The answer is basis. Who said we're solving a system here? Please be careful. Please be careful. And even if we were solving a system, this wouldn't be the problem that we have certainly has a solution. We have vectors that span a subspace, and certainly some of them form a basis. So it's not even an option not to have a solution. So the basis is the first two vectors. Why? Because the first two columns have pivotals. So please read what is written in red very, very carefully. So the basis is 1, 3, -2, 2, and 2, 1, 0, -1. We started explaining the Gauss elimination method by explaining that by using it in order to solve systems, right? However, the Gauss elimination method can be used on any matrix, regardless of whether that matrix happens to be the augmented matrix of a system or not. But just to address your question anyway, if this was the augmented matrix of a system, which means that the system would have been what? The system would have been, if it was, it's not. But if it was, and it's not, again, I'm saying, the system would have been what? X plus 2y is equal to 5, 3x plus y is equal to 5, -2x plus 0y, or plus nothing for that matter, is equal to -2, and 2x minus y is equal to 0. That would have been the system. Would the system have a solution? Absolutely. Absolutely. When does our system not have a solution? Our system doesn't have a solution when you find a row that looks like this: 0, 0, 0, all zeros, and the very last one is 1. That's when the system doesn't have a solution. Okay, this system will have a very nice solution. Okay, can I tell you what the solution would be? Of course I can tell you. The solution would have been x plus 2y is equal to 5. So I go now to the augmented matrix. These are excellent questions that you're asking, by the way. These are excellent questions. And then the other equations are all zeros. So I know that y is 2. I plug it into the first one. I get x plus 4 is equal to 5, which means gives me that x is equal to 1. So x is equal to 1 and y is equal to 2. And you can check it. You can plug it into all the equations and you can see that. And there was another question as I was answering this that said the following. Isn't that what I said right here? Please read it again. We need to read, right? It said, to extract a basis, we form a matrix that has the vectors as its columns, right? Okay, we did that. we perform Gauss elimination method and bring it to row echelon form. We did that. Here's your row echelon form, right? The columns that have pivotal elements, that's the first and the second column have pivotal elements, correspond to the SOCT4 basis vectors. That means that the vectors who went to the first and the second column, which means this one, are the ones that form the basis. That's all. That's what it says, right? I didn't do anything more, anything less. I did exactly what is prescribed right there. Okay, and you will have a homework problem to do this yourselves. Okay. I understand there's a lot to unpack, but if you look at what we have done in the last two lectures, which is absolutely crucial, is we have explained the Gauss elimination method. And today we performed it a few times. And so far we can do what? Solve systems. Find inverses. Extract a base. From a set of generators. Please understand that in each of these cases, you need to adapt the Gauss elimination method to the specific requirement. So in the first case, you perform the Gauss elimination method of the augmented matrix, and then you go back to your variables, right? In the second case, you perform the Gauss elimination method, and then, if possible, you make it into a reduced row echelon form. And in the third case, you perform the Gauss elimination method and you take the vectors that correspond to the pivotal elements. That's all. Okay, and this is crucially important. This is crucially important. That's why I'm setting it on this basis. And you know what? Since we have time, let me actually solve the quiz, right? So somebody asked me to do the quiz. I have time now. So why don't I do the quiz? Okay, so here's your quiz. We wanted to do Gauss elimination on 2, 4, 6, 2, 1, negative 1, 1, 1, 3. Okay. Please send me elimination as the keyword. Please send me elimination as the keyword. And let's do our Gauss elimination here. Okay, so I create a pivotal, 1/2 row 1. And this gives me 1, 2, 3. Everything else stays the same, right? I never mix multiplication by number with the other operations. And now it's time for me to eliminate 2 and 1. So I do -2 row 1 plus row 2 and minus row 1 plus row 3. And what do I get? I get 1, 2, 3. I get 0. -4 plus 1 is -3. -6 minus 1, that's -7. And then I get 0. -2 plus 1 is -1. -3 plus 3, that's 0. So far, so good? What do I work with now? What do I work with now? Here's what I work with. I leave behind me the first row and the first column. So I create my pivotal, -1/3 row 2. You could also bring -1, 0 on the top and multiply by -1. It's up to you. I will leave it up to you. It's the same thing pretty much. So 1, 7/3, 0, -1, 0. And now I eliminate -1. How do I eliminate -1? Minus row 2 plus row 3, which will give me 1, 2, 3, 0, 1, 7/3, 0, 1, negative. Oh, it's not. Sorry, this was -1. Yeah, it's not minus, it's plus. Sorry about this. It's plus. Right, so it will be 0, 7/3, And now what do? So I'm done with second row, second column. So no, so what part am I working with here? And all I need to do is make this pivotal. So I make this pivotal. 3 7 row 3. And that gives me 1 2 3 0 1 7 thirds 0 0 1. Okay, and that's it. Now, had you used a different row operation at the second step, you could have had another row echelon form. So the row echelon form, let me see, let me be careful at what I'm going to say here. I was about to suggest that it's not unique. Well, no, in this case, no, it's going to be the way I did it. Yeah, it's not going to be any different, actually. I think unless you work with a different first row. So let's say on the first step, you put on the top the third row, 1 1 3. It's a possibility, right? So you swapped row 1 and row 3. Then you would have got a different row echelon form. Okay. Questions? Yeah, of course it is still correct, because look, I want you to understand this is an excellent question. So the question is, I said that if, for example, you had used a different pivotal in the very beginning, you would have got a different row echelon form. And the question was that correct? Of course it would be correct. And what I want you to understand is that we don't do Gauss elimination method in order to just do it. We do it for a specific reason, right? And any Gauss, no matter how you do it, no matter what pivotal, that's the only difference that it will ever make, how you choose your pivotal. Okay, so no matter how you choose your pivotal, the answer to any of the three problems that we have done so far will be the same or at least equivalent. So in the case of solving the system, it will be absolutely the same. In the case of finding inverses, it will be the same. In the case of extracting a basis, you may end up extracting, somebody could have even put the columns in a different order from the very beginning. So it's not that you will always have a unique set of generators among a set of a unique basis among a set of generators, but certainly you will get this same, the correct. The 3 echelon versions, I'm not sure I'm following here. As I said before, it's very, very simple. What I said before is very, very simple. If in the very beginning, you started by swapping the 2 rows here, if you swapped row 1 and row 3, the top row would have been different. So eventually you would have got a correct row echelon form, but a different one. Okay, that's all. That's the only flexibility that you have in this method is the choice of the pivotal element. Exactly. Yeah, remember, I made a remark about this before. I said that in many books, you're going to see that the pivotal element is not required to be 1. I do want you to make it equal to 1, both for recognition purposes and because in the case of solving systems, it's going to make your life much easier. Okay. So there is another question here. What happens if you have? Yeah, I'm afraid so. This is the way we gave the row echelon form here. Yeah, absolutely. Yeah, I'm not grading the quizzes, so that will be. So there was the following question: is this matrix in row echelon form? If it's not, what do we need to do? And the answer is no, it's not in row echelon form, this 0. It's not in row echelon form. Why? Let's see why. So this is pivotal. This is fine. This is perfectly fine. Everything below it is 0. Oh, sorry, this goes 1 actually. Otherwise, it is in row echelon form. This goes 1. This one So in other words, once you're done with the first row and the first column, you should work with this one. And here's your pivotal. I circled it. Yes, but what is below it is not zero. So what do you need to do in order to bring it to row echelon 4? Here you need to do minus row 2 plus row 3. And then you will get 1, 0, 0, 1, 1, 0, and this is row echelon. And that's it. Okay.
I have a question. So the homework asks that students and I asked to put in row echelon form. Let's say we put in reduced row echelon form. Is that still correct?
It is still correct. I mean, but you're doing more than you're asked to. Okay, still nobody should be taking any points off for you doing this. You're just doing more than you're supposed to do. Okay. And the reason I want you to understand the difference between the two is that in this case and in this case, you don't need to reduce to row echelon form. The time you need to reduce to row echelon form, and this is pretty much the only time you will need it, is in this case to find inverses. So why do the extra work? Okay, that's my only objection to this. You don't really need it. Okay. Any more questions? Okay, then that will do it for us. I remind you that my office hours are in 10 minutes. I hope you all have a great day.